friends sometimes.
So Anna got her PhD in Warsaw in Chinese College Group in December 2011.
Yeah.
Okay. And she's been working during the last year in this European project on silent emotions. And I think this is what she's going to tell us about today.
Yeah. Thank you very much for. I would like to thank you, Professor Miguel, for inviting me here. It's a pleasure to be here, and I hope, as the topic of my presentation is scaling and correlation in dynamic of communities. As Professor told, I work in project cyber emotion, and this is mostly where the results came from. So in my presentation, I will attempt to cover 4 topics in the following sentence. I will first I will introduce to the habit of passive users during website browsing, especially some strategy during news portal browsings. And then we switch to active users, which are write some message in internet, and I will talk about collective emotion in cyber communities. We define what the collective emotion are, and I will try to answer the question if it's possible to observe affective interactions in communities. Later I will discuss transition due to preferential cluster growth of collective emotion in online communities, where I will closer look at the mono-emotional threads. These 2 parts are very connected to each other, and I will talk about specific problems from this. And at the end, final, I will talk about negative emotions and the role of negative emotion in some discussion and how they change length of discussions. In the work of scaling of human behavior during portal browser, we ask ourselves 2 questions. Do users have any general habits when they browsing the portals? Do they employ any strategies? I will try to answer these questions by applying these methods like data analysis, numerical simulation, and some theoretical description. Oh, sorry. So, the data was collected from 2 Polish portals. It's enough to say that A is one of the biggest and B is the largest Polish portals. There are news portals and the news portals. Sorry. If I pronounce something bad, you can correct me anytime. So as I say, our aim is behavior of human behavior disorders, and I need to make my small reservation that the Hypernet network it's not the same as network that we built from the activity of user jump from one subpage to subpage to another subpage. What is subpage? Subpage is not a single article. Sometimes it can be part of portals that we can measure traffic. And the data structures allowed us to reconstruct the sequence of visits by every user and build the network in this way. I will come back to the network.
So Portal B has 4 million users every day?
Yeah, in one day.
But you only observe 500 subpages.
Yeah, it's number of subpages. From that time, from 27th, probably now they have more than 1,000 subpages because they're growing, of course. But these data are from 2007. There was small changes from 2009. It was about 1,000 subpages already.
How do you register the unique users?
With cookies.
With cookies. Okay.
With cookies, I know that it's not the same as real users, but for the short time, that's one day, it's not such a big divergence between real users and cookies. And in Poland, it's in that time, 27, users don't have such many different version of mobile phone, different twice computer, something. It can be some more close to the real number of users than today, I think. Okay, and build the network is very simple. We have nodes that is subpage. We have weights which are in somehow related to the traffic between two subpages. And as we observe, the reciprocal relation between traffic go to the node J, and from node J we decide to analyze undirected network. So the links is the sum of traffic from node I to J and from J to I. And the basic properties from the network, as we analyze here, the weights and strength distribution. In both cases, we observe power law scaling, and it's quite the same exponents from both portals. And also, when we change the date from even in it was 2007 to 2009, the characteristic scaling looks the same. So it's general stability properties. And as I say, the main problem was to analyze the user behavior. So how they change the subpage, how they jump from one to another, and how many unique pages were visited by the users. We here have the distribution of unique subpage. It's exponential, so it's decay fast. It's different in the case of jump distribution. It's more complex, and these lines are not fit. Some theoretical application of this function that was obtained from the very simple statistical rules.
So what is that?
And it's number of number of jumps. How many times you click, how many times you change subpage.
It's only the number of jumps, is not how far in the structure you go. So it's only the number of jumps.
It's number how many subpage you visit.
Okay.
Doesn't matter if they repeat or not. Okay.
The number of clicks that they use.
Number of clicks.
Right.
That was counting in this machine from the cookies, because it depends where you counting the cookies. You can have some small subpage that is connected to each other. Yeah.
So
But
you
it's
have
not-
500 pages, right?
Yeah.
And there are people who do 1,000 clicks.
Yeah, there are not people from this end. Of course, there are machine. That I focus on the first part of scaling, fifth part of regime, because at the end we have some machine that was sent to crawling something at this website.
Two things I don't understand why I want to point out. First, so the most likely thing for one person is to click only once.
Yeah,
So they just go there.
yeah.
So and the second thing, which is the relation between n and c? N is the square root of c. Sorry, the other one. N is equal to c squared. No, you obtain. I mean, the second distribution P of n has a weird shape.
Yeah.
The distribution, no, the formula. The formula is
The
kind of
equation.
weird, right? And so it comes from the previous one by a change of variables.
Mm-hmm.
So it's down.
Yeah, it's
So
but
the change is z
to the
n equals to z squared.
yeah.
Why? How?
Yeah. You have very good. Exactly. What I applied in the previous analysis was this finding from data. We found in data that the relation between average number of unique subpage versus number of jumps is square root. And at first look, it was very surprised for us, because we don't have one-dimensional systems. We have network with many connections, and it's looks like diffusive process on one-dimensional chain. Why? we will try to find the answer for these questions. And first, very naive version was like that apply random walk on the weighted network. Maybe the kind of weight in somehow force walker to repeat it such many pages. So we take the structure of the network and we decide that transition probability will be proportional to the weights of links. But unfortunately, it don't work. It's not enough to reproduce the process that was observed in data. So we closer look the strategy of users, how they visit. We thought that maybe the homepage is somehow special, that the user will come back to homepage many times. So we analyzed the probability of comeback, that one step is website, homepage, something different, homepage. How many times in the whole dynamic we observe that situation? And we have the probability is about 0.9 here. And what we check later, that it's not larger from different subpage. So the mechanism of comeback is everywhere. Doesn't matter if it's homepage or not. So we decide to apply this process of comeback, which is maybe the using the button back in the simple way to our simulations. So then we have topology of network, the transition, and also the probability of comeback P star here. And after this, we can call our walk as self-attracting random walk. And the red crosses are the results of simulation. So you see that it's fit to the data very well. Of course, only in this regime that we have the scaling. But can we describe this problem also theoretical if it's self-attracting random walk? Why not? So standard probability of transition, and then the stationarity occupation probability. But I need to stress that this probability can be only used for stationarity problem. After some times, after a walk, don't remember the first step. But is this in the case in the portals? I don't think so. It's not in the case. At the first part, we don't have stationarity problems. But anyway, we apply this. And then we can describe the average number of unique subpages, but using this parameter D, which is the fraction of vertex of string S visited by a random walk at least once after time n. And this is from general problem without adding this come back. But when we come back, we change this D for some kind of D star, which is different from the factor 1 minus P star. And in general, in our results, we have this difference that we observe this 1 minus P star here. And how it looks when we compare to the data. Numerical simulation, red, self-attracting random walk from the equation here. It's blue here and black line, and data are black. So it fits to the numerical simulation, but unfortunately, in this regime, that its data are already losing the scaling. Yeah, but anyway, I think it's somehow explanation of the mechanism that was observed during portal browsings. At the end of this part, I want to analyze also the problem that why user behavior in such way. In this problem, I can just only make some suggestion that it may be from that kind of situation that they have some a horizon of interest that is, for example, sports, and they follow to only these subpages, and the fashion is not important from these users. Or maybe they use some how to transition pages, that they have to go through some pages to another subpages. Yes?
During their visit to this portal, some pages will be updated more frequently than others.
Yeah. And there can be some just transition from the portal. So the problem is that if the portal managers really need that they transition from one page to another. Yes, because they can show them more advertisement. So maybe they don't want to make the portal in that way, that is more effective way to user, because this is not effective for they to sell the advertisement. But there are only my idea of this problem. Finally, I would stress that the self-attracting random walk is the process that can be. With this process, we can reproduce the behavior observed in the data.
This is very similar to Higgs law.
What?
Higgs law. So this is basically the Higgs law measures the number of different words
Yeah.
as the number of words in a book, for example, right? So
Yeah.
you have 10 words, and then how many are different? And then you scale set, that is the number of different
Yeah.
web pages. And it's a similar power law scale in that
Yeah.
case. So here you claim there is the memory to return to the previous web page. So in the case of the words, that would be the probability to use the previous word you have used. So I have no idea. So it's something like that has been used for explaining the Higgs law in the case of Lewis. So I don't know if you are familiar with that, but I'm saying
No, I am
basically
familiar.
that this law is very similar
Yeah,
to
okay.
the word frequency thing.
Yeah, I know.
I don't remember what kind of models have been used in order to capture that, but I see that there should be,
Yeah.
maybe there is a connection between the two things.
I
So-
understand the problem.
But I don't know if you have thought about that or.
Okay, let me switch to another part. And as I say,
So, Gordon, can we go to the first transparency of this part? Yeah, can we go to the first transparency you showed us in this first part? Okay.
You check if I answer for these questions.
Yes.
Yes, there are some strategy of comebacks. If they have some habits, yes, they have some specific horizon of interest. It's okay? Yes?
When I go to a news portal,
Yeah.
the front page is updated very frequently, and when I click on some specific one, it gets updated less frequently.
Yeah.
So I traverse up and down because if I go back, then I'm likely to see something new.
Mm-hmm.
So
I don't have the information how quickly they change the information, but it's from one day. But yeah, there can be many changes on the homepage, definitely, but not from the yeah. Maybe if with this information we have to make some new version. Yeah. You're correct. So if I now can go. Okay, thank you.
The talks here are rather interactive.
Of course. So now we can go into active users. So first was about passive users that just only read the internet. Now I will talk about readers, users that write in the internet. So what's about collective emotions? There are results from interacting between users. It's not a sum of emotional groups. Yeah, it's something more, something that came from interactions. And what I want to show here is that we can observe affective interactions between the users in communities. First, I need to stress that as psychoscience say that most of transform emotion is non-verbal. It depends how I speak, how I look, how my voice changing. But anyway, if the internet is good place to show the emotions, if I answer you this question, of course you say yes. How many times I see this post with horrible news or with a lot of expression. So even that, if it's limited way to show, we found this way and we express our emotion. Moreover, it's not only talking about expressing, but we also talking about exchanging, about some interactions between these emotional users in internet. And the example of that we can find in the Twitter revolutions and also in social media during elections on now 2012 in USA. So there is example when the internet played very important role in changing and communication and also in creating some new attitudes, new way of looking for some problems. Okay, and this is some example also from DIC, because I will talk about data from DIC. This is very short about some privilege in USA. It's also very emotional if you can read. But my analysis, its first part is data analysis. I will talk about 3 data sets. Data was collected by our group from Wolverhampton, and we have BBC data, DICS, and Blogs Forum. There are very different communities with very different users, but we have more than 4 million comments in general to analyze. And what is the most important, all of this data was emotional annotated. This means that also our partners from Wolverhampton classify this emotion. It's one of the version of classifier. If you are interested, you can go to the website of the Wolverhampton team with Mike Tywell, and there are different variants also. So it needs some training data. So there are some users, real human, who detect if this text is positive, negatives, or neutral. And then there is a black hole for me, but the machine that change after learning this machine, this can annotate the emotional in the text. Of course, it's not perfect. Of course, it's the problem of irony and something different. Yeah, but it's better for short text than for longer, of course, when we talk. So the Twitter is very good for annotating in this way because it's very short. And for me, in the later analysis, I will be talking about the clusters. What is the clusters? The main definition. It's that it's a chain of n consecutive messages. Yes?
This sentiment algorithm, you take into account the context of the message, or I don't know, for example, you have a positive word, it would be interesting, but then you have the positive word, like interesting.
Huh?
It's interesting, but you have not interesting.
Yeah.
You consider
Yeah, of course, the not of all negations are taken into account. But as I say, the variant of the Wolverhampton team still developed this classifier. And when I do this analysis some times ago, probably now the version of classifier is better, and so on. So they also try to cut the sentence in some part to find that the last part is the most important, because sometimes you say, oh, I love this word, but I need to kill someone. Yeah, but something doesn't matter.
So that would be neutral?
you understand that some ironic, some problem that at the beginning you say something, but conclusion is totally different. Yeah, maybe my example is strange. Yeah, but in this version we focus on 3 states, and for me it is the most important. So we have emotional cluster of size n, which is n consecutive message with the same emotions. And we have 3 states, so we can have positive, negative, and neutral clusters.
So this is about one topic?
Oh yeah.
Different people are talking about one thing, or?
Yeah. BBC Forum is about religion and ethics, and also news. These are general comments of some stories, of some photos that was put there, and blogs is very difficult to say. It's about many different problems, but we analyze the clusters in one discussions, in one thread. Okay, we have some chain structure of thread. It's natural structure for the blogs. It's not natural structure for BBC and for Dix, because there you can address your message to some guy. But in the website, the way of presentation is linear. So we decide that this will be the best way. And what's for us is the most important is time arrow. That this guy have opportunity to look at this message, and this guy was, when he writes this message, was not opportunity to see the next message. Or the consecutive is the most important here when you put your message. And we have positive, negative, and neutral clusters. As I say here, is negative cluster of size 3. And here is the example of discussion from religion and from BBC Forum, and we've annotated some clusters. And even at the first look, you see that shuffled data, in the shuffled data, the size of the cluster are less than in ordinary data. Yeah, we have some phenomenon of grouping message with the same emotion. We have some interactions between the users. To close analyze this problem, we prepare a growing probability of cluster of size n. So how large is probability that after 4 positive messages we have another positive message? And what's happened when we have 4 positive messages, 6, 7, and so on? This probability will increase with n, because red data are from positive message from BBC, blue are negative, and black are from this shuffled data, to show that we are not observe this problem in shuffled data without this interaction, without this correlation between emotional users. So we can say that this power law increasing of conditional probability can be also write by 2 parameters, which alpha is some kind of strength of interactions, how is changed, and PEE is the conditional probability of appearing at cluster 2. So it's also taken from the data. So only one parameter here is the alpha that I picked from this value. And as alpha is less than 1, we have some preferential cluster grow, which is sublinear. For me, it's somehow similar to general problem of preferential attachment, but in the clusters. And what is also needs to stress that the alpha is less than 1. And
you see that you have a maximum number of clusters. I mean, after, I don't know, 10 positive or 15 positive messages, people might get bored or do not have any other message.
No, the statistics. The problem is of the statistics. Some part here, because I agree that we have some final size effects on this discussion will end sometimes. Yeah. And also it's a problem that the last point is every time 0.5. Why? Because you have two clusters with size, I don't know, 81 is here, 80 with size 80, and one will continue and one will be end. So the last point is every time 0.5. Because I have only two states there. What's about cluster distribution? And this way I have cumulative, in this plot I have cumulative distribution. And the blue triangle are from data here. This behavior shows that there are some large clusters. And the problem is that know how large they are, but how different it is comparing to the random process. Because we have the random process, and it's the first line, don't predict such large clusters. And also Markov process, which is here with some information from data, which is a conditional probability. We have one-step memory. It's better. It's here is quite good, but it's still don't predict that large clusters. And finally, when we apply this preferential growing clusters, then we can find, after some calculations and some after some calculations, we have these equations, which is also very nice because we have only two parameters, which are alpha from the previous slide and PEE, which came also from the data, and it fits to the data very well, which reproduces the character that we observe in cumulative distribution. And I will show you that it's not only for DIC, this is for DIC, it's very nice, for BBC also very nice. There are some problems with blocks, because in the blocks, the way how they was preparing the data, they only take that discussion that was longer than 100. So these are not completed.
How can a cumulative distribution grow?
Cannot. Then I will say that this function that was for me analytic finding in this way can play a role, a cumulative, only in somehow regime.
So this thing is not guaranteed that it decreases with n?
What?
This function of there is not guaranteed that it decreases with n?
Is
No,
decrease.
the expression, the analytical expression.
Analytical expression.
It doesn't decrease always?
It decrease, not it's because this factorial.
Yeah.
And this is the problem for a large value of n, but it's not in the case that we have regime.
No, but I'm sorry, I don't get it. So this expression says the cumulative is equal to something. So I assume that it's an exact expression. So if the assumption is the equation that is on top of that,
Yeah. Okay.
then how can, it's impossible, because by construction.
Yeah. Look at this. I apply this probability.
Yeah, but I don't.
No, but this is the problem, because this probability can reach 1.
And then?
And then I will talk about in the next part. When we have 1 here, of course, this is a problem with cumulative distribution.
No, the cumulative distribution, even if at some point the probability is 1, then you will reach a plateau.
It can be more than 1 even.
More than 1.
Let's put some value of n and alpha in PAA. For BBC, it can be, because we have some artificial line from this theoretical, and from that reason, it's also not good for blue. Only for that value of n, that is, it's depend on alpha and p and n. If it's enough small, like for this data, everything is okay. But when we have a different value of alpha and p, it's not. But I know about it.
So
It's not that I'm using probability that is even larger than 1. I know that it's a restriction of this method to some regime.
No, but how to do is that the probability is this, the minimum between this value and 1.
And the maximum value of n.
Well, it doesn't matter. I mean, you can put the larger and then restrict to 1.
Yeah.
So in that case, the probability is 1. And then it will just be flat.
Yeah, that will be ending somehow this point. We will not have this regime. Maybe it's a better way to don't show this kind of plots and not make you stress.
Yeah, this is something completely different.
Okay, we'll have strength of interaction, which is alpha. We have different value for different emotion and for different data set. And what we see is that BBC is very negative data set, and also this is very negative. And there, the positive emotion, the value of positive emotion of alpha is larger than in negative. Because in negative it's not such, the slope is only slightly different from constant. It's different in blocks, definitely, where the positive emotion are in somehow the most frequent. And when we say it in one plot, we see that those emotions which are in minority have a larger interactions between each other. It's not such simple because we're talking only about larger value of alpha. It means that they have more likely grow their clusters. So we have rare emotion creation, stronger ties. This is some main conclusion from this part. And of course, when we put together the parameter alpha and conditional probability, we can find very simple linear function which show us this anti-correlation between alpha and p. And especially this correlation is important from the program that we talking before, because when this value is up this part here, we have problem, mathematical problem, and in this regime everything is okay. Yeah?
N was the size of the clusters?
The size of clusters?
With an N.
Yeah.
Does the length of the discussion somehow relate to the amount of emotion?
Length. I have answered for these questions at the last slide. Last. It will be simple, sorry. Okay, of course, it's the problem that we don't observe clusters of size 40 in the discussion which have 20 messages. But here I present the distribution that was prepared only for discussion with length 20, 50, and 100. And the character of distribution is the same. So even if we not apply the problem of how long is the discussion, it's for general description don't have matters, don't change anything. It's obvious that we don't observe cluster larger than in one done discussion, but the stationary is the same for part of discussion that for general. Is it a good answer? Is it okay? Okay, I will come back. And here, I also want to persuade you that there are some interaction between users, that they are different users. It's not like one crazy guy 100 times, right? I hate this word. And this is negative emotion, of course. So we analyze how number of unique users we have inside the clusters. So it's not a linear relation, so it's not 100% of unique users, but it's about 7 unique users for cluster of size 10. So we can say that there are some interaction between the users. It's not only one users who are writing the sentence.
Can you go back just a little bit?
Yeah.
No more. For instance, it's probably not very important, but it's something to do with the data analysis.
Yeah.
When you plot everything in a log scale, okay? You use log scale everywhere, even though it doesn't seem necessary. It goes from 0 to 1, so why you use a log scale? So is there a reason to expect a power law dependence on all these matrices? So the conditional property increases as the power law of the chain length n. Is that the best fit you can get? Power law, or you expect that the power law
it's
to
best
be...
fit.
It doesn't look very good, either.
Yeah, I know
But
that
the
the regime is not such long. I agree with this.
However, have you tried other ways of
Of
thinking?
course, we have tried
The power
linear,
law is
exponential. I watch it in a different scale, and we also think very long how to find the measurement of errors. And this is quite problems because this is the conditional probability, so we have only some number of appearance. And this was difficult to find a good way to show the errors. But the fittings is the better, the power law. We're checking different. Okay. Okay. Yeah?
This previous slide. So you said you interpret alpha as strength of interactions.
Alpha, yeah, it's some kind of...
So how did you arrive at this interpretation?
Yeah, because it's somehow ability of this emotion to create longer cluster comparing to the random. Because we compare to the random, the probability of appearing negative emotion is very high, but the difference between random length clusters and observed is not such large like in positive emotion. We have very small number of positive emotions in this discussion, but when they appear together. They are in some groups.
So it's not a strength of interaction in the sense of sociological theories like strength of ignites or is it?
Yeah, maybe no.
To what extent they could be two posts at the same time? Meaning that if somebody...
We have the information about the second.
It takes a while to write something there, and if there is a comment on the news which is very popular and whatever, they could be writing the comments basically without the opportunity to see the previous one. Because it's being read and attended.
But how many situations we have that?
No, that's my question, because there's how close they are the post. I mean,
Comparing
do
to
you
the whole...
discriminate, for example, assume that you have a cluster of positive opinions and in the middle there is a one that is negative and it continues positive, but the second positive has been written at the same time than that one. That means that the cluster could be bigger.
Yeah. Of course, there's one of the problems, but comparing, for example, the occurrence of classifier and different kind of problem that you think that is not true for the what classifier say, but any random error are not our problem, because we see that the random error cannot create the clusters. Our aim was to show that we observe some interaction between the users. Maybe in somehow the errors change the numbers, but don't change the description of general problems. And that I want to stress that we observe some collective interactions, even if there are some random problems, maybe they destroy some clusters. I also check the cluster with some noise, but the description is similar. Yeah, if you understand that maybe this message is noise, and the general application is very similar. Okay, can I
Go ahead, please.
It's about half.
Don't worry. We like discussing.
Okay, so finally, the conclusion of this part. I hope that I managed you that we have some preferential cluster growth, which are such good that we can explain the cluster distribution. And as I said at the beginning, the cluster distribution with such large value of cluster size, it's some sign that we have affective interactions, that there are users which interact with each other, and this is our definition of collective emotion, which they are interact with each other, so we have some collective emotions. So now I will talking about my recent work, which is already in reviewing physical review, and we will see. So the transition due to preferential cluster growth of collective emotion in online communities. Now I will talk on the problem of discussion that became mono-emotional, that in somehow from some point of, at the moment of discussion we have only emotion with positive emotion or negative emotion, and can we observe that kind of situation or not? First part is numerical simulation, then some description, and only at the end I will show some results from data. So now let's go to the model, which is two states model. So I reduce neutral emotion. I have only positive and negative emotions. And we have two parameters, x, which refers to short memory. I just changed the notation for conditional probability from the previous part, and alpha, which can be some kind of long memory strength interaction if you don't want. And we apply the mechanism that was found previously in the data. So let's make the simulation. First, the comments is random. Then we have applied this mechanism. And what happens when the probability became 1? It means that we have such cluster size, critical cluster size, that after this cluster size, in simulation, we never have different situation. Only we will have 100 message of positive post. It means that never be different. So how looks this situation for? It depends, of course, on the x and alpha. And here I have to say that generally the x and alpha for different emotions can be different, but I will focus on the situation where they are the same for both emotions. Sorry. So, critical cluster size, it's just function from n to the alpha from different value of x. And what's about critical time? Okay, I also need to stress that we say mono-emotional thread, and this MET is the short name for this. Critical time is time, how long we have to wait for observing these critical clusters with that value of x and alpha. And this is the simulation from between critical time and alpha, from both emotions have the same value of alpha as on this scale, and the x is equal 0.5.
Sorry, I didn't understand. So the model is that your simulation is that you're based on those conditional probabilities. You set one set of emotions, and the next one is chosen from that probability.
With this probability and so on and so on. And to more precisely analyze critical time, we decide to analyze inverse critical time. And here we have lambda versus alpha for different sides of the systems, but it don't change anything. The behavior is the same. Of course, for a larger system, we have we need less value of the restriction of alpha to observe the order situation is not such high for the green line, which was a very long simulation. And to describe this problem in mathematical equation, we see that this inverse critical time is equal probability of finding critical clusters, because we have one-dimensional problems. So the probability of finding the cluster is that how long we have to wait. Yeah, and as this probability was already prepared in the previous part with some small changes, especially the normalize factor was changed here, and finally we have such a description of gamma which are here. This red line fit very well to the data. Yeah, as I say, the length of don't have the length of threads, how long the system was simulated, don't change this behavior, but of course it changed this behavior with this fraction of order realization. So if we have the simulation of 100, probably for some value of alpha, we have all realization which are not ordered. And when we increase the size, we observe that order behavior appear for less value of alpha, but this increasing with alpha is also continue increase. So what's changed is a slope of this line, and when we analyze this, so the tangents of this line is represented here as a red pole, and we see that with larger system size this increase, and what's happened with so the transition became steeper, and when we take some value, some special value of alpha, for example, when the number of realization which are order is equal half, here is violet point here, so this properties decrease with increasing the value of L. And that situation is true in a finite system size. It's different in infinite system size. What happens in infinite system size? Or in both situations, because here I present the relation between a fraction of realization versus x, we see that we have discontinuous transition for infinite size. So for every value of x and alpha larger than 0. But for 0, we have, don't observe, of course, red fat. So it's very quick changes only in this point that is below to 0.
Let me say, because why are you saying that this is continuous transition? Because this is, for instance, the case for a calculation transition. When you have a small system size, and usually you see this kind of curves of the calculation transition, and then when you increase the size, usually these kind of curves become more and more sharp. So is there any reason why you believe that actually in infinite size you have this continuous transition?
First we analyze the value of function, because everything was, as you see, the error can be also write as a function, and we calculate the limits of this function when we go to what we have changed. And also there are some signs that this is going to infinite here. And when I talk,
this is the slope of these curves are actually related to,
yeah, it's
not preparation related with the susceptibility, but it's not related directly to the
yeah, I agree, it's some kinds of situation, but for example, when we take the one-dimensional easing model with external force, you have transition when you have external force larger than 0. So in somehow, I think about these examples. Yeah, it's a difficult problem here to find what we really observe, and sometimes the naming of previous work is not, how to say, they are not in the same way. As to say, this problem would say that it's not discontinuous, but there are some problems that in similar situation they say that it's discontinuous. I will not say about explosive percolation, because there is also the problem if it's continuous or not discontinuous. Here we decide to say that this is discontinuous, and we will see what say the referers from Physical Review A. I will in second. Now I'm waiting for a second response. So in first they say that. Yes.
So they will compare you after two.
One. No.
I will compare you.
No. They have different. They need some data application, and I prepare the data. Yeah.
I have a more basic question. The critical point is defined in the limit of system size going to infinity. The question is, the critical point there goes to 0?
What?
If the
value of alpha goes to 0.
With the going to infinity. No, that figure was perfect.
Okay.
No, the other one.
No, this one is one.
Yeah.
This one.
Yeah.
So if L goes to infinity, alpha critical goes to 0?
It's not alpha critical.
Well, it's alpha 1.
Because it's very difficult to define alpha critical, yeah?
Let's say the alpha average value, whatever. It goes to 0? It goes to 0?
Let me
It's not close, it's approximately close to 0, but it's not go to zeros.
But have you checked whether it's potentially goes to 0 over, I mean, like a model?
Okay, that's what the one I think.
Well, if you are asking about these transitions, you get all that.
Yeah.
let me
Let
me moderate that. I mean, it is good that there are many questions and you're answering them, but I think that given the time now, we should let her try to summarize the rest of what she wanted to present. Okay.
I have another part.
Okay.
So, very quickly, I will go to the data in this problem. Or do we observe order discussion in real data? Of course, in real data we have fluctuations, we have a problem of some random users that you're talking about. So we decide that if the cluster is larger than critical clusters, it means that for us it's order discussion. So we found that clusters in blocks, but it's not appear in BBC, and it's also connected to the problem of value of P. In BBC and Dix. And the last column, this was a result of simulation when we apply real data structures. And we'll see that there are more, of course, but because there are no fluctuations here. There are examples of met phase here, where the critical size for is 31, and we observe some cluster which have 72, and it's at the end of the discussion. So there are some states that will not change at the discussion. Of course, there are limited representation, but here we have even 35 from block 06 and neutral. Why we have this situation in block, and why we don't observe this situation in BBC and Dix? And to answer this question, I have some complex, to say, plot when we have alpha and x for r equal 0.5. So this is how this is the requirement for alpha and x to obtain half realization order with different length of system. The white is larger than 10 to the 6. This is between two. This line is for L 10 to the 3. Sorry, 10 to the power 3, and for less than 1 to the 2. What we observe that these points are from real data. So there is not in the case with half realization. They are just points from real data, from value of L, alpha, and to be honest, PEE, not X. But we see that in the block data, the value of alpha and the PEE are such enough large that they only need length of system about 2 to the power 3. So this is that we have in the block data. There are some discussions that have 1,000, but when it's needed for BBC, for example, 10 to the power 6, we don't have such long discussion. So from this reason, we don't observe the med phase. Okay, so I hope I persuade you that we have some order discussion. There are some continuous changes, and it's maybe some discontinuous changes in infinite size. And I will go to the another part. This is mostly from data analysis. I will persuade you that negative emotion has special role in internet. As you probably know, in the real world, we try to avoid emotion, negative emotion. When someone is screaming, when someone is crying, we try to avoid. I don't talking about the problem if there are someone who is very close for us, then we want to help them. But generally, from negative emotion, we try to avoid. And we try to avoid negative emotion. But how it looks in internet, it's the same or not? And I want to say that it's definitely different. Negative emotion in internet have some power to motivate another people to write another message. And here we have data from BBC. It's the average emotion versus number of comments in the thread. So how negative emotion have influence for this discussion. We have some value of emotion at the beginning, which is also negative 0.44, but the end is 0.42. So they use some negative emotion during the discussion. So this is some kind of fuel for discussion. Here we have some window shuffling and analyze average emotion in window shuffling windows of 10. So that's why there are the number are not 0, only 0 and 1. And it's true for different discussion about when we have like 20, 40, 60, or 80, and the end is at the same letter. So if they lose the negative emotion, they stop writing. So the negative emotion is somehow fuel for the discussion. And here we have some kind of prediction. Let's take first 10 comments and see how long this discussion will be, comparing discussion with different emotion in this first comment. And we see that if there are more emotional comments in the first part, the average expected length will be longer than in situation that we don't have emotion in first part, or we have not such many emotional comments. So emotional beginners of the threads usually lead to longer discussions. Probably observe this in your personal using of internet. Okay, so very short about BBC activity. So we have some A, which is total activity of users, and D, which is the local activity. Where local activity is activity in one discussion. How many posts you write in one discussion? Of course, these are power law, but go on. let's see how it's changed average number of unique users during the discussion, for longer discussion. When we have longer discussion, of course we have more loyal users. It means that here is normalized number of unique users, so it's number of unique users divided by length of the discussion. And you see how it's decay. So for longer discussion, we have more loyal users. And how these loyal users express their emotion. If you are very active in some discussion, if you are large value of D, it means you are more negative. It is not in the case when you are generally active in the forum, because there is no correlation between average emotional and value of A. So it's only problem when you are focused on some discussions. And here we have the average emotion for discussion versus length of the discussion. Of course, the longer discussions are more negative. Why? Because in this discussion we have loyal users, which are more negative. And we understand why the longer discussion have to be more negative. Okay, so finally we have negative emotions, which are the fuel of discussion. And longer threads are more negative. To conclude all my presentation, so I hope I persuade that this is some kind of self-attracting random walk that can be responsible for behavior of user in internet. We have some interactions, affective interactions in internet communities, and we can observe some mono-emotional trait, and also that negative emotion can be as a fuel for discussion. In this part, is observed in BBC forum. Thank you.
Thank you, Anna. There have been many questions. What I would propose is if there is any urgent, important question, let's have it now. If not, there will be time for private discussions to discuss with them. No urgent. I was discouraging them. Okay, then, thank you, Anna.